Good afternoon, everyone, and my talk will be about an instrumentation aspects uh, related to the workshop, and I'll try to be brief and fast and not so much boring. I know everybody's tired. This 21 signal can be detected by very different ways, and if it is originating very local to us, then we go through this top path. We can have very simple telescope, and if not, they are coming from very far away distances, then we need some complex telescopes and very sensitive telescopes and complex data analysis methods. If the signal, although it is a very rare signal, and if it is very local to us, if it is from our galaxy or very near to us, simple instruments such as the student gadget, a horn antenna, can detect this signal. And what can we do with this? We can actually derive the rotation curve of our galaxy. It's very easy to construct. It's probably a couple of weeks, or a 2 months, 3 months project if you are attached to an electronics lab. These are post-MSc students made this instrument just out of cardboard and aluminum foils and so on and so forth. And in a rooftop in a city environment, this telescope works well, and it actually produced a paper. And they were able to measure two geometries depending upon whether we are looking outside the sun's radius from the galactic center or inside. So the geometry, the top one was used here, and measurements produced remarkably very close to what one would expect based on other measurement that exists. Red dots are the measurements made from this work, 3 months effort. So anyone can actually pick up this 21 centimeter signal from our galaxy and produce these rotation curves, and which is surprisingly easy. So if you go not just simple telescope horn like telescope, if you have slightly more sensitive, slightly bigger telescope like a single GMRT dish or a 10-meter dish or a 6-meter dish, we could actually even see the intensity variations as we move the telescope along the width of our galactic plane. Or if you could point to Andromeda, we can even see this double horn structure. And these are easily possible. While it is easily possible, we do have sensitive telescopes such as the GMRT, much more interesting observations that can be done. Of course, everybody knows GMRT has operating frequencies all the way from 125 to 1460 megahertz. So what is shown here are some of the observations. One of them is a deep observation, and we can pick up weak signals, 21 centimeter profile, and also some other very clever techniques have been used to get the profiles not just by time averaging, but also spatially averaging. It's a clever technique of stacking the images appropriately to detect these signals. So while these things become possible, when you want to look at it on this path, the signal is originating from far away distance. It goes through complex processes, and the detection becomes very challenging. However, very simple telescopes could also be used to detect these signals, which is where we come across core, zebra, edges, Saras, and the future ones too. They are basically very simple telescope, just similar to the construction is similar to the horn antenna that I have mentioned, except the analysis and the perfection by which they will have to be built, that becomes a little harder, more involved, but it's not very expensive. Again, it just needs a dedicated amount of effort to build them. I have listed few in the morning. Samir's talk, we had more have been listed. So I have picked up only 3, the core, edges, and Saras, because they draw some parallel information for us. At least I was able to note few things from their work. which I wanted to highlight. We know there are some news about some of these results, but I'm not going to go into any of that. The slides, consecutive slides are going to tell about some of the instrumental aspects related to these instruments. All these instruments, I've been working hard to pick signals in this regime of the redshift, these features. And although it's very easy to build these instruments, we did have technology 15 years back, 20 years back. Not many attempts have happened. Only now the community is actually lighting up to see whether these experiments are what doable. So the first of the one, which is from core, and before I go there, I just want to give a brief feel for what these instruments do. These are basically total power receivers in some sense, slightly advanced. They look at the signal arriving in an antenna, and some kind of a pre-detection processing happens, amplification, low noise amplification, filtering, and then there is a simple square law detection. A signal power is detected, and they are integrated over some time and recorded. Basically, at this point, we are able to get the envelope of the incoming signal, and we average it to sufficiently and record it. And the integration time decides the bandwidth over which we will be able to get independent samples from the information that we are recording. Very simple to construct. The one which you saw for the horn antenna, the 21 centimeter on rotation curve measurement work, used a simple total power receiver chain of this kind, but it used modern electronics like software defined radio, SDR module. But the basic principle is only this. The problem here, we may not have much control over. We can't be just doing averaging. Current radio astronomy scenarios demand dealing with RFI, so we have to constrain the averaging time so that we don't wash the signal with any RFI occasionally that is coming. So we need to be concerned about it. And excessive average cannot be done. We need to be careful. And also, if there is a gain variation, why would gain vary? If the instrument has to work over day and night, temperature varies, ambient temperature varies, and usually amplifiers, their gain varies, fluctuates with time, and there can be even power supplies whose power fluctuations can affect the gains to vary. So, which is little difficult, and it can make the variable sensitivity levels of the instrument at different times of the day. And if the beam is simple, it's very narrow, or if there is a point source in the sky which is very well calibrated, whose power intensity that we can receive is well known, we can point it to the sky sources, the calibration sources, and do some kind of a deal with these fluctuations. But normally that is not the case. It's not available. So people go and use another kind of receiver. All the Saras core and edges, all these instruments use this principle, where there is a extra stage which makes use of, there is a typo here. This multiplier is just square law detection stage. Okay. So it's just an extended box. So the antenna signal is switched away to a fixed calibration signal, basically a resistor, 50 ohm resistor, or a noise generation electronics. Between the observations, that will also be passed through the same system and recorded. The switching is often done at frequencies at which it is sufficient to deal with the slowly varying any temperature variations and so on. So in principle, what we are going to get is always a reference signal is monitored in such a way that we do have account for what may be the variation that may be happening in the system. Of course, this assumes the reference source is not going to be varying over time, it's going to be constant. And most receivers that we have heard about, edges, Saras, all of them have this built in. So I'm going to go and show 3 of those instruments. Core is one of the oldest along the time when edges also was working out the principle for the detection in the MRO, the current SKA site. This development also was taking place. This is a spiral antenna. You'll have two arms, go up, and you'll have a reasonably uniform frequency response. For UR detection, it is required to have a uniform frequency response across the frequency of interest. It worked for those who are comfortable with the redshift number 11 to 5.2 to 11 redshift, or 114 to 228 megahertz. Interesting thing to note here is they kept slightly a calibration band around 200. They don't expect any emission of interest from the 21 centimeter or any fluctuations, and they kept band about 200 for a control purpose, which seems to be missing in the current designs. So what they have is a noise source antenna and the kind of a switching. It's kind of a thing which allows flipped signal, 180 flipped signal through one path, and normal and telescope signal through another path. And it is slightly advanced from Daiki. It not only does this noise reference, but also takes care of any local coupling. We get the signal perfectly in the antenna, but on the way, before we record it, we can actually spoil it by injecting RFI into the system from the local environment. So it takes care of that part of it, because an inverted signal, and they are multiplied and averaged when it comes out. Now going into the details. And edges, if you go on the other hand, has a very different antenna, a squarish shape dipole. Actually, people spend a lot of time designing the antenna part of the, and that's one of the area where lots of student projects are possible, where this antenna connects to two parallel circuits, and along this way it goes through the noise source, noise reference. You can see they can be switched in. Either the noise can come, it's just exact similar to the Daiki switching that I have shown, except for this additional path that they have to worry about, the antenna reflection and so on, which is normally not done in the site. It's done in the lab, and they are moving to do it in the observational site in the next revisions. So it had two receivers, low band 50 megahertz to 100 megahertz, which made news in the recent past, and there is a 90 to 190 megahertz instrument that has been tried out for a long time. So what is missing in this instrument? If you go back and see this core instrument, this local coupling that can happen from neighborhood, that part seems to be missing in this. But I'm sure there is a way they have dealt with it. And now moving to Saras. Saras has an interesting antenna, and just checking the time. Sorry. Yeah, Saras has an interesting antenna, and that floats on water. One of the things that antenna gets affected by, it's a reflection from the ground. When the ground becomes wet, moisturized, and there's underground water, one side is more conductive, other side is not, and so on. It can affect the beam, and the beam can tilt, and there can be some kind of a frequency dependent aspects can set in. So that is what is tackled by keeping it on a water of certain salt level and so on, and depth that maintains the uniformity of the ground plane. Yeah, it's kind of an extended ground plane. Ground plane is very short here, actually. You can see it. So this was tried for the Saras experiment. I'm also not going into the historical background of which other instruments have existed before Saras. So once again, if one looks at it, Saras has a similar calibration noise source. There's a crossover switch and two parallel systems and signal condition unit, where what is not shown is the signals are multiplied again, and local noise coupling is removed. And interestingly, this instrument uses a fiber connection. Go back to edges, it's a coaxial RF cable, and the description of the core is not there. Here it is a fiber. The fiber floats on the water all the way to somewhere here. The receiver will be kept. That's the way the connection is made. And now we are through with this basic instrument. This is the way the instruments have been designed and used, and the complexity of the instrumentation comes only from making it work very finely, nice, and so on. Otherwise, very, very easy to build. Now, if you go into cosmological distances again and want to do slightly better than these simple instruments can do, we go into sensitive, much more sensitive and complex telescopes, which again will make use of more complex analysis of the data, more novel approaches to data processing, and so on. So I'm going to again give only few examples, not going to fully go into everything. I've learned about many of these recently. So please feel free to stop me anywhere if you find have a question or a comment or a clarity is required. So again, these are some simulated images. So these telescopes are designed to probe these regions in their spatial distribution level at which we should be able to get information. Now, what drives these kind of new next, the fourth category of antennas is the concept called interferometer and with a correlation receiver. Whereas core and the other type edges, they suffer from typically self-induced noises. Okay. They can actually add up, sum up, and raise the ground level, and sensitivity level can go away. In a correlation receiver, correlation is a very powerful tool that is used left and right in radio astronomy instrumentation, much the same way Fourier transform is used. It's very, very powerful. It can actually give an output if there are two antennas are involved and the signal is conditioned, you amplify it. Signals come very, very weak. They come in typically, I don't know if you are aware of the milliwatt, and it's minus 120, 130 dBm level. And they are all amplified, filtered, and then bandpass filtered, and they are multiplied and integrated and recorded. So in this process, in the process of correlation, removes any independent antennas related additive noise. They will get reduced in the process of, so the receiver gain variations will have very less effect, even though you leave it on for 24 hours, 48 hours, few thousand hours, and so on, if you want to observe. And this is the way to easily build signal chain. So random phase variation, on the other hand, will affect. Okay. While the gain variation doesn't affect these instruments, the phase variation can affect a lot. That's why ionosphere, phase scintillations, and things like that, for an interferometry observation, we need to be careful about. And no switching is involved. Now, what the two antenna signals, when we multiply, it produces what sometimes called as a fringes or complex visibilities. So diagram, simple diagram like this doesn't show the complex correlator, but there will be two different correlators to check for the correlation in the orthogonal signal basis, sine correlator and cos correlators, and we would get a fringe shape like this if there is a passing source above the antenna looking direction. So we record these fringes, and that form the bread and butter for image making. And we don't have not just two antennas. Typically, in an interferometric array, there can be as many as, in the case of GMRT, 30 antennas. In the case of the future SKA, there can be 512 stations. Okay, so that's the power of an interferometer. And what happens here is, once we record these visibilities, we can go towards left or right, and you go to the right, and you can produce these images, beautiful images, do the Fourier transform with FFT sky coordinates, and we get an image of the sky produced. And interestingly, with the cosmology, every frequency channel, if you are interested in the redshift, and that's going to tell us the time story for us. So the cube will have a three-dimensional depth-wise information. And if you go in the other way, instead of worrying about the images, you go in the other way and just do the Fourier transform along the FFT channel, frequency channel dimension, and we get into producing nice components like this, which separates out the principle of the Fourier transform, separates out things which are nearby, far away, and so on very nicely. So we get into the delay spectrum and all the nice information that we have discussed about it over various other talks and so on, and other things that I have not shown also probably will follow this path. So most of the byproducts after the visibility can be stored and can be processed in many different ways to either go this direction, that direction. So now coming to LOFAR. LOFAR was originally designed as a model for a future square kilometre array, and LOFAR has a very nice looking, the greenery is nice. Not only that, even the antenna, the principle by which they all work. So you will see this kind of a nice looking antennas. By the way, this 50 megahertz to 200 megahertz is a very hard, 300 megahertz is a very hard frequency range to reach for an antenna. Build a simple antenna, 50 to 100, twice the frequency, 100, 150, 2 times, 3 times, 4 times. Likewise, we go, the antenna design is not possible. A single antenna cannot respond so well. So LOFAR divided the antenna into 2 segments. Okay, low frequency, huge antennas, and high frequency, little shorter ones. So these 2 antennas essentially form the LOFAR's main antenna sensors, and there are a large number of them. I had put in a lot of details here. I'm not going to go through all of them, except to say that this antenna is not spread in one country, and it's spread across a lot of places in Europe, and form essentially a huge antenna that can be as big as the dimension of that area that it's going to be. And even recently, Italy has joined and is building one of the stations. The station is a collection of these antennas combined together to form, look at one direction. The signal from these antennas are digitized, processed, software, and it's a software telescope. The emergence of the first software telescope, in quote, within quote, was seen from LOFAR. Blue Gene, the IBM computer, was first time used to process the data offline, and entire telescope operation was done in software. That paved confidence and way for the future telescope to follow this. Now, going from LOFAR, we have the HERA. It's also making news of late, and it's supposed to be a low-cost cob web kind of a infrastructure. It's a wood poles. By the way, India also we have some telescopes with wood poles. So wood poles, plastic PVC pipes, net, and so on, to form a very huge 14-meter wide individual antennas with a hanging dipole in the top, and not steerable. It can only see signals when it comes on above it. Whereas in LOFAR, we can form beams to reasonable directions in the sky. And once completed, this HERA will have a multiple such dishes forming a hexagonal shape. Okay. And it will form a big dish of about 300 meters across, and the collecting area will be large as well, and it would be one of the very interesting telescope for the UR science. And due to, normally people don't build interferometers like this, because in interferometer, any antenna spacing which is identical, repeated, or getting avoided. People go for a random positioning of the telescope. GMRT has all antennas are spaced very differently from each other. SK also follows that style, whereas here is a complete uniform grid. What it gives? Large amount of additional sensitivity that may be required for a short baselines, which is of importance for the UR science. HERA, as you heard probably from other talks as well, as going through a stage of, every instrument has got its own initial problem, and what happens here is a mutual coupling, antennas probably talking to each other, which is not desirable. People know probably how to deal with, and working out a strategy. In my opinion, what's going to happen is they're going to probably develop new algorithms and so on in real time, so that they can deal with it while doing observation, which may be a very useful tool for SKA. Coming to the last one, which is an MWA. This is a telescope that we have spent time building the receivers and also in early commissioning, and also a member of this group for a long time initially. The telescope consists of a nice spider-like antennas. What we call this particular group consisting of 16 dual polarized bow tie antennas as a tile, and there are 128 of them to start with, and it's located in the Western Australian desert, where the human population is very, very less. It's the same place where the SKA is going to be built. SKA low telescope is going to be built. So now SKA MWA is getting upgraded to form the Hera-like hexagons with additional antennas and few more long baselines. For low frequency telescope, calibration is a problem. There's not enough sources that we can spot because the beams are so big, and one needs long baselines to resolve them. And it's being a trade-off. You need short baselines like this, which means antennas should be sitting closer for the UR sign. But if you want to use antennas, you need to calibrate them. And any other signs that we need to do, we need longer baselines and so on. And sorry, I'm coming back to that slide. So they are extending the antenna number of antennas from 128 to another 128, making it 256. The original goal was 512. Due to some funding problem, they restricted at 128. Now they are going to 256. And now coming to SKA. This is the last of the interferometer that I want to talk about. That is the upcoming telescope. Two parts of the telescope. One in South Africa, which will have a dish antennas. 192 antennas. 196. Yes, and 64 of them will be locally built by the country, and the remaining by the member countries. And the other telescope, which is a low frequency telescope, which works, I'm going to go from this diagram to the next one. That will be built in Australia. That will work from 50 to 350 megahertz. I was mentioning it's hard to build an antenna which will work all the way from 50 to 350. Whereas in the dish antenna, they are covering 350 to 15 gigahertz, but they will change the feed. The dipole here will get changed every time we go for a new frequency, much the same way how GMRT works. Whereas here, the same antenna will have to work. So it is built out of multiple dipoles in some sense, each responding to a different frequency range. The bigger dipole at the bottom is a Christmas tree kind of an arrangement, a tree with the top part responding to 350 megahertz and the lower part responding to 50 megahertz. And all of this actually will be digitized, and the number of dipoles that will be digitized is 131,000. It's been never been done before like this for any instrumentation. So it's a huge work, and enormous amount of dedicated work will be required in the field. So people are trying to reduce that by making the system work properly so that they commission it works. Output from these antennas go into what is known as a correlator beamformer. The beamformer and the correlator are responsible for producing the image product, image cube, visibility cube that I showed, and also to do another job to look at the sky in multiple directions. So this telescope can look at 1,500 directions simultaneously. The low frequency telescope can look at 500 directions simultaneously. The multiple directions are used for survey applications. Data from here goes through imaging path and a non-imaging path. Imaging path is where the UR science data would come, and the non-imaging path is meant for the pulsars and transients, FRB and other kind of VLBI and other kind of activity. And then the data gets into global distribution, and ideally we should also get copy from this green box of the data when it works. Telescope configuration. The antennas are called Scala, SKA log periodic array, SKALA, Scala. Now the current version is 4.1, I think. So the antenna themselves is about this tall, about this wide, and you can see 256 of them are located here, and that is called a station. And the stations are located in a 40 kilometer radius, and about 50% of which sits in a 1 kilometer square area. And it involves enormous signal processing. and no moving parts. Entire operation is done through electronics. And I'm going to just show this to give a feel for how the electronics will look like. What is used as the heart of this digital processing is known as a field programmable gate arrays, and they are very massive parallel processing logics. They are the ones responsible for producing the first level Fourier transform and the beamforming of the scope, and also the correlation, everything. And that's how the boards would look like. So I'm going to what is happening in the site now over the time, almost close to the end of my slides. These antennas have been kept in the site and validated before the actual telescope will be built. A station will look something like this from the sky if you look at it. And they were checking with the MW antennas as well as the antenna designed for the SKS Scala antennas. The top part is a Scala path. The bottom path is a validation based on an existing MW antennas. A station built out of MW antennas, here a station being built out of Scala antennas. These validations are taking place and people are continuously analyzing it. I'm going to go into then finishing up to say while we are there, RFI is one of the things that affects and makes our life very challenging. Increasing RFI we keep talking about. In our analysis, we never take into account the RFI. Some parts of the band of interest for UR may not be there. I'll show you in the next slide. Available, may not be accessible at all. You have to go to the moon or some other parts of the, to do observation in those places. Because of the increasing number of things, we feel very happy about it. There are cycle rickshaws to cars, everything electric. And ISRO launches 36 satellites on one go last 2 weeks back. And we are so proud of it. And Starlink, SpaceX launched so many satellites. What's happening here is they want to have 650 satellites for global service. OneWeb is a UK company for internet. It is not that satellites themselves are bad. There are out-of-band emission from satellites. What you see here on the left is the band observed by Berman et al. During the early edges experiment in 2010 in the MRO site. Bands from 110 to 190. There are some intermittent RFI. Obviously, this is not instant shot. It's probably averaged over a few hours. Now, the current scenario, I don't want to overemphasize it because at that time may not be any work, site work happening here. Now, probably people are working also. But it's a typical of what one would see in the band of interest to us. 50 megahertz to 300. This is the data, actual data collected through Scala. Using the SKA receivers in the site over a long time in the world. So you could see how would we ever observe anything at all in some of these places. The notch which is also seen here around 76 megahertz, that may be an artifact that will get fixed, but the RFIs will not go away. And the part here coming from the US military satellites, which nobody can affect, can avoid, even GMRT suffers from this. And these are some communication satellites, some weather satellites. The good news is it's still RFI excision can be applied. If you apply, then we can start seeing a good band. The data that we need to process may have to be processed to this level, and that's the scenario. So now, I'm just showing another slide here. This is the slide showing we have these many observation sources to be looked at. And the sources go from east to west in the sky. And now these diagrams show the tracks of the source, how they will move between this period in October to next day, how far they will move. So now what you see on the vertical lines of the satellites, they are crisscrossing. Sorry. So imagine if you're doing a UR experiment and the beam is filling this part. All these satellites, we are unaware of it. Anywhere on Earth, they are there. So how do we detect them? How do we avoid them? What do we do with that? We have to be careful about it. So that is what this slide is supposed to tell about. And then I think in future, we need to be more careful with this RFI related thing also included in our analysis. That's where we need realistic data and need to worry about calibration algorithms. I think that is an area where the new instruments are showing us gain, beam shape, direction related, and also aspect related to polarized sources. And what we do even when the large amount of data volume comes in, probably we need to apply novel schemes. It's just like an instrument. Two instruments can be deployed simultaneously. Okay? When there are problems, to see whether is it something or SARS, two instruments. So likewise, some novel approaches required. And also I added this even before our discussion. It's useful from the point of view of get a feel for what the scenario is. You need to set up local data access facilities in radiometer. So I end here. Thank you.
Anyone? I don't see any. So I can pose one. So for Indian context, do you think we should go with the interferometer or global?
It's good to go with interferometer with a provision for both a hybrid approach. Have the I assume the question was suppose we have to set up anything in a simple instrument.
Right.
Set it up as an instrument. For some reason, people have not set up as both. So we should have a provision, a provision to have an interferometer. It also records.
Okay. Any other question? Okay, let's thank Prabu again. Thank you.
One question.
One, okay.
So I have a very naive question. So I mean, I have seen different shapes of antennas in your slides. So like horn antenna and a conical shape antenna. So what different shape does? I mean, what are the implications of having different shapes?
Yeah, the shapes are actually will have an impact on the antenna look direction and how uniformly it can see, and how uniformly it can see the same area across different bands. So it will have an impact on that. For example, the log periodic antenna, Scala antenna, may not be the uniformly having a gain across the full band. So when the antenna is designed for a broadband, so these shapes have a relation with how the beam response will be in the sky. You want to pick up equal amount of power from all directions it sees. So one direction it's like less, on one frequency less than other frequency. Our spectral response, anything we do on the spectrum, frequency axis, will have to be taking that into.
And another thing, can we do interferometry with horn antennas or Saras-like antennas?
Yes, we can do that.
Okay. Any other? Okay. If not, let us thank Prabu again. Thank you. Wonderful talk.
Thank you.
Our next speaker is